Okay, so it's 3 p.m. already, but since no one has joined, I'll wait for a couple of minutes and then we'll get started. All right, since it's time already, I'll get started with teaching. So hopefully others will see the video later on. So welcome to this week 7 TS session on optimization methods for civil engineering. So today's topic of discussion is some introduction to metaheuristic optimization. And then we'll look into the one of the metaheuristic optimization technique, which is called as the genetic algorithms. So to broadly discuss first the topics that I'll be covering today. First is a bit of the limitations of this classical optimization technique. So this sir has already discussed in the class, but I think I'll briefly talk about it before diving into the metaheuristic optimization. And the content of this week is, I think, pretty simpler than the previous week's contents because I think I just looked at the assignment and I could solve all the questions in like 10 minutes. So, and there is no numerical as such in this week's content. So it's mostly concept based, and also probably I'll take one or two examples and try to see if some of the numerical examples will help you in the later next week's classes as well. Okay, so this is the first topic that I'll discuss, the limitations of classical optimization. Then I'll briefly talk about the meta-heuristic optimization and how you can overcome those challenges. So meta-heuristic optimization and its advantages. Then next, I think you have learned about briefly about this genetic algorithms. So genetic algorithms I'll discuss as well. And within this, there are three operators I think you have learned. So the genetic algorithm operators. So this is where it gets interesting, and I think if you take some numerical examples with this, so you can solve such problems. So the first one is the selection operator. The next one is the crossover operator. And finally, the third one is the mutation operator. So we'll talk more about it in the context of binary encoding. So all this discussion in this week's content will be in the context of binary encoding. In the next week's discussion, it will be some real encoding that will be there and that will be discussed. So these are the main topics that have been covered in this week's classes. So first to talk about the limitations of classical optimization technique, you know that you have found out those necessary and sufficient conditions of optimality based on certain assumptions that the function is continuous and differentiable. But what if I give you a function which is not continuous or differentiable at some of the points? So maybe there are some breakpoints in the function, or maybe there are some region where the function is not differentiable, or there may be some discontinuities. So in that case, it gets tricky to optimize those kind of functions, or maybe you are solving some mixed integer programming problem. There, the feasible points are not continuous itself, so you are dealing with some discrete points, and the solution is on a lattice in that case. So it's difficult, and you cannot just apply those gradient information and solve such problems. So that's one thing. Then we have seen in case of unconstrained optimization problems, and like we have used some Newton-Raphson's method, or maybe some other techniques like region elimination techniques and so on. In that case also, you need like certain informations about, like you need to provide uh, to the optimizer, maybe the code you have written, that you need to give some starting point and you need to optimize your function from that initial point. And in that case, it might happen that if you want to find out the global optima, it's not guaranteed that you might get it. In case of convex function, obviously, the local optima is the global optima, but that is not the case in case of non-convex functions. So you can typically use those methods that we have discussed, but you may be stuck at some local optima in that case. But based on your problem setup, you might be interested to get to the global optima. So that's the challenges that the classical optimization techniques face, and you can have, like overcome it using some meta-heuristic optimization that I'll be talking about today. So in case of meta-heuristics optimization, so let me write down this first, the classical optimization limitations. So as I have already told, the limitations are the functions. The function has to be continuous and differentiable. And then what you have to do, convexity will help. Convexity in case for global optima. Yeah, we have one person joining. Okay. Yeah, hi Pankaj. So I was discussing about some of the limitations of classical optimization techniques, and we'll get started with the meta-heuristic optimization and genetic algorithm in detail soon. Okay, so as I mentioned, this classical optimization problems have this limitations that the function has to be continuous and differentiable. Then convexity is required in order to find the global optima. And the third one is that you need to provide a starting point in this case. And based on that, if your function is not convex, you might end up at some local optima and you may not get to the global optima, but that's not our goal. We need to get to the global optima. So that we'll do using the meta-heuristic optimization. So the meta, okay, so we have another person joining. Okay, so meta-heuristic optimization, this can overcome all the limitations of the classical optimization. So You don't need to provide this starting point, or you need your function need not be continuous or differentiable, and convexity assumption is also not required. So in this case, I think Sir has also provided some examples in the class. So what you can do, uh, so let me draw some functions. So suppose you have a function like this one, some sort of sinusoidal function with some damping. I think I've not drawn it properly, but suppose there are a lot of optima here. You can notice that there is this is a local maxima, this is a local maxima, this one is another, and so on. So what you have to do is that if you use classical optimization technique like Newton-Raphson's method, if your initial solution is somewhere here, you might end up at being here, but you're not getting to the global optima. So those parts, like this tricky parts, will be avoided using this meta-heuristic optimization, or maybe your function itself is not differentiable at some points. At this point, this function is not differentiable. So how do you overcome those things? Or maybe your function is not defined like continuously throughout an interval. Like your function could be something like this. So there could be some breakpoints in between. So those things like will be overcome in this meta-heuristic optimizations. Okay, so to get into more specifically in the discussion of this genetic algorithm, so I think Sir has already discussed about this the foundations of genetic algorithm, like survival of the fittest and all those things, and the relationships with biological sciences and so on. And then, like with Darwin's principle and everything, I think he has already discussed. So I'm not going into the history or the main background of it. So my interest is mostly to discuss about more about this genetic algorithm, the algorithm itself, and also the operators that are involved there. And yeah, so there are no numericals as such in this week's assignment. So let's see if I can just take one or two examples and try to solve those by the methods that have been discussed in the class. Uh, yeah, since two of you have joined, maybe this is a good time to ask you, like, do you have some specific questions? Maybe it can be related to this week's content, or maybe some of the previous week's content. From that, you can also ask questions like if you have some doubts related to some assignments that have been already evaluated, and you have some like doubts or complaints or anything, you can tell me right now. Otherwise, I'll move forward. Yes, yes. Sure. Go ahead. Which one? You just mentioned me the first few lines of the question. I'll understand. Then. 7. Question number. I'm not here, able to hear properly. Actually, I don't have that question open. So can you just tell me the first few lines or something of the question? I'll be able to. I don't have the numbers. Not able to hear you properly. Can you just type it in the chat? That will be helpful. Assignment 7, questions 17 and 18. Okay. Uh, is it those questions which is like tournament selection type and the best and the worst population will? Is it that one? Actually, I don't have the numbers. Okay, then I'll just open it. Okay, yeah, you have said correct. Okay, yeah. So, since you have asked this already, I'll just go directly into that because I think I've already gone through the lecture. So, you have this genetic algorithm, and you have one of the operators which is called the selection operator. And within that, you can have multiple ways to select your solution. So, one of the operator, like one of the method is this tournament selection. So I think the question asks you that if you use a tournament size of three, what is the best solution in the population pool will have? So uh, how many copies of it? I think if I'm not mistaken. So that's the question. So let's see how we can solve this. So suppose the solution, the number of solution that you generate in this case, probably that's six. So suppose you have some binary encoding of say 1010, 1111, say 1100, then maybe it can be 1001. Then what I have missed, I think I have missed 10. Uh, this I have already covered. Yeah, so maybe let me write some zeros here, 0100, 0101. So suppose you have this six binary encoding. These are the initial say solution that you generate, and maybe you are trying to maximize your function in that case. So what you can do first, you can convert them into decimals. So these are your decimal values, and as you can notice, this one will have the highest one. And if your function is directly related to this, so then your f will be also higher for this one. And corresponding to that, since you are maximizing this, your fitness value, fitness function will be maximum for this one. So this is the best solution in the pool, suppose this one. Then what you have is that in the tournament selection method, everyone plays with certain solutions. So you can think of as like in a tournament, say in a cricket tournament, one team plays with another, and maybe some grouping is also there. So suppose your tournament size is three, and probably I'll group this three together at first and this three together. So this three will play against each other, or maybe playing against the other two sides, or maybe other two solutions in this case. And then since this is the best one, so suppose when you use a tournament size of three, so let me name them. This is the first solution, second, three, four, five, and six. And two is the best solution that is out there. So in the first round that you play, this is round one, then you take three solutions from here. Then two will definitely win in whichever three that you pick because that's the best solution. And in another match, so another three setup solution will be there. Some other solution will win. Then round two, in one of the matches or one of the tournament that like the round that you play, like suppose there you pick this three solutions together. Then also this 1111 will be the best solution, and this two will emerge as a winner there as well. And then from here you generate two solutions. So generate two solutions. And one of the solution is two because that's the winner. Here, this is winner and solutions. In round two, you also generate two solutions. And suppose you want this population size to be constant, like you had six, you want to generate six solutions. So you will play three rounds here in order to get six solutions. So here also, suppose you pick, say this one, maybe this one and this one, then also this 1111 will win that round. So two will again win, and you will also generate two solutions here. So since you need to play 3 rounds here, and in whichever way you pick or choose your 3 solutions so that it plays against each other, so this best solution will always be the winner in every round. And that's why you make 3 copies of this because you play 3 rounds. So is that clear? This is the I think question, and I think this has also been discussed in the class as well. So even though the assignment question is exactly the same, I have almost given you the answer itself. But is it clear, or you have doubts? Okay, this is the 17th question. What is the 18th one? Uh, is it uh, is it related to that mutation, like some mutated beat of the string that is asked? Is it that one, or is it something different? Can you just confirm? Because I don't have the numbers with me right now. I just have the last year's questions open. Decode value. Okay. Mm, okay. The decoded value of the binary string. Is that the one? Yeah. So I think that's the one that you are asking for. Okay. So yeah. So let's see how you can decode the value of a binary string. So suppose I have given you this 1 0 1 0 1, something like this. So what you need to do, suppose you need to convert it into the decimal. Uh, and that's your decoded value in that case, which is also called dV here in the slides, I guess. So what you need to do, corresponding to this, you can have 2 to the power 0 here. Since you are dealing with binary numbers, so that's why this 2 comes. Corresponding to this 2 to the power 1. So from right, you just write the powers of 2. And next, what you have to do, you just multiply whatever number that you have with this, uh, the 2 raised to some powers that I have written, and you need to add it up. So the decoded value will be 1 times this, plus 0 times this, plus 1 times 2 square, plus 0 times 2 to the power 1, plus 1 times 2 to the power 0. So if you add it, you will get probably 16. From here, you will get 4, and from here you will get 1. So your decoded value here is 21. Suppose I give you some other 1, 1, 1, 1, 1, all this ones. So here you have to multiply this by 2 to the power 0 and so on. So I think how many bits you have right now? You have 8. So I think this will be 2 to the power 7. So yeah, 2, 3, 4, 5, 6, 7. Yeah. So you just now added all these powers that you have to add and you will get the decoded value. So is that clear? I think that's pretty simple, I guess. Yeah, okay, great. Okay. So since you have already asked this, let's do the opposite thing as well. So this is kind of a conversion of binary to decimal or the decoded value, whatever have been mentioned. So so how you can just convert your decimal to binary? So that's another tricky thing. So I think that's not been discussed in the class as well. And I don't know whether that's required or not, but let me just discuss this in this context. So this decimal to binary you can do. Suppose I give, uh, say, 37 as my, say, decoded value, but I want the actual binary string associated with it. So what you will do, you just take this number 37 and you just divide it by 2. You get this solution 18, and then you have this remainder 1. And then you divide it by 2, you get 9, remainder 0, divided by 2, then you get 4 and remainder 1, then you divide it by 2, you get 2 and remainder 0, and you divide it by 2 again, you get 1 and you get remainder 0. And finally, this 1 will also be there. So probably this 1 comes here. So let's see. So hopefully I've done it correctly. Yeah. So this remainder will go here finally. Sorry. So now what you'll do, we'll go from this side to this side in order to get your binary value. So corresponding to this, the binary value should be 100,101. So let's see if I have done it correctly or not. So corresponding to 37, which is the decoded value, I'm telling you that this is the binary you should get. So corresponding to this, 2 to the power 0, corresponding to this, 2 square, and then 3, 4, 5. So it's 32 plus 4 plus 1, so that's 37. So that's great, you have got it correctly. So this is the method of doing it. You just divide it by 2 and just keep track of the remainders that you get. And then you just backtrack everything and you will get your binary string. So yeah, I hope this is clear as well. So any more questions, or maybe I'll just take the assignment problems because assignment problems. Okay, what is this? Yeah, we talked about assignment questions. Okay, okay, yeah. Some answers was wrong. Yeah. So yes, so I think the main key of the course he will prepare. So we had talked with him. I think he will prepare some solution and will post it. And about the questions that were wrong, I think that has been already communicated. Maybe the question was wrong in some cases, or maybe the answers were wrong. So yeah, that thing have been brought into notice and probably will be taken care of. And yes, the exam is, I think, in the next month. So yeah, before that, the solution should be posted. Yeah, so yeah, we'll also communicate with him this week, probably. Okay, okay. So since there are no more questions, okay, I will probably see the assignment problem of this week. Since there are not many numericals, I'll probably just discuss some critical points related to it, and let's see. So I think one of the question asks you that there is this crossover. So this selection is now somewhat clear for you that I have discussed this one example of this tournament selection. So let me just discuss about this crossover thing. So this is crossover. So now suppose I give you two solutions, say 1, 0, 1, 0, 0, 1, and then I give you another solution 1, 1, 0, 1, 0, 0. So now what I tell you that suppose the crossover site is given. So suppose crossover site is 3. So in that case, what will be the newly generated solution? So what is your or what are your newly generated solutions? So let me ask you this question. So when I say the crossover site, so I can name it from here as well, 1, 2, 3, 4, 5, 6, or I can name it from this side as well, 1, 2, 3, 4, 5, 6. So which tree to pick, this one or this one? Do we count it from right or do we count it from left? Is that clear? Like, let's see to know this. Like I'm telling you, will this be a crossover site or will this one for this problem? Okay. Left. Yeah, correct, correct. Yeah, exactly. So what you have to do, so suppose this is the third one that I have given you. So since this is the crossover site, so you just break it from here itself. So whatever you had from here will go here and this one will come here. So your newly generated solution will be 1, 0, then this part will come and this one will have 1, 1, 1, 0, 0, 1. So this is your newly generated solutions. So these are your new solutions with crossover. Okay. Okay, so I think you will get one question related to it. It's pretty simple. It's just counting it from the left side that you have to do. But in case of mutation, what we do, in case of suppose one problem I'm giving you. So in case of mutation, let me just go into the problem itself because that will be easier for you. Suppose, yeah, suppose I have a solution 1, 1, 0, 0, 1, 0, 1. Okay, so now let me just erase one. Okay, anyway, so now suppose I tell you that the fourth bit in this problem has to be mutated. So let me give you this example. Suppose the fourth bit has to be mutated. Okay, so now in this case, which one is the fourth bit? Do I count it from this side or from this side? Uh, so what do you do in this case? Is it this one or this one? Okay. Is it too simple or like you haven't read it or anything? Um, okay. Yeah, correct. Right. Yeah. So I think it's too simple. So in that case, what you do, you count it from the right. So your first bit is the rightmost one, second bit is the second rightmost one, uh, and so on. So let me erase this one, not to avoid this confusion. So when you do mutation, what you do, you just change the bit around. So if it was 0 before, you make it as 1. So now this one is your fourth bit. So what you will have a new solution, is this one. So this is your new solution. So yeah, so this crossover technique is essentially a local search kind of technique, and mutation can move your solution, like it can make it larger, a lot larger. Like if you're changing, suppose your leftmost bit was 0 and you're making it as 1, and you have some n bits in the solution string. So in that case, your decoded value will improve by 2 to the power n minus 1, something like that. And if your n is pretty large enough, that will like give you a large solution. So you're kind of jumping your solution from one part to another. That might happen with mutation. So typically, I think in the class it has been discussed also that you don't keep the probability of this mutation to be high. You just need to keep it less so that you don't jump around and miss some solutions or something. And in case of you have a good solution and crossover technique is used, and in that case, this crossover probability has been used with some 60 to 95%. And in that case, you are just your solution to the children is pretty close to the parent. So I think with this concept, you might get a couple of questions as well. Okay, so let me see what else are there because I found it pretty simple this week's assignment, mostly concept based. Okay, so let me discuss. I think there was one question, some 10th question or something. Let me discuss that or maybe similar type. So what you have, suppose I give you some binary string, suppose a population, suppose your population is 10100, maybe the next one would be 01010. This is 11010, and maybe the fourth one is say 01110. Okay, so now this is your population. These are your 5-bit binary strings, and then you have to find out the strength of fitness of maybe chromosome. So these you also can tell them as chromosome or solution, whichever you want to call it. Suppose I want to know the fitness of this solution or this chromosome. So in that case, what you can do, suppose you have also been given that the fitness function. So suppose this is your strength of fitness function. This has been given as fx. And suppose your function value is itself fx equals to x in this case. And this you might call it as capital F of x. That is also fine. So now how you can calculate that? So first thing that you have to do, you have to convert it into decoded value or the decimal value that I have talked about. So this corresponds to 2 to the power 0, 2 to the power 1, 2 square, 2 cube, 2 to the power 4. Okay, so in this case, the first one will have this 2 square and 2 to the power 4 added up. So that's 16 plus 4, that's 20. The second one will have this 2 cube and 2 added up. So that will be 10. The next one will have the 16, 8, and 2 added up. So that will be 26. And the last one, so what is the decoded value of last one? Let's see if you have understood or not, since you have already asked this. You can type it in the chat. Okay. I hope you all are listening because I asked a simple question. Just decode this value. Yeah, the concept is not that difficult. You just have to multiply this and then add it up. I hope you will understand even if you are not later when you solve the problems. Right now, I don't, I think you're not listening or something. Okay, so this will be 2 cubed plus 2 squared plus 2 to the power 1. So it's pretty simple. So that's 8 plus 4 plus 2. So that's 14. Okay, so next, what you have your function, which is equals to x. And you can write it itself like, uh, suppose you are not using some projections or something like that you can do using some x min or x max. So I think there is one formula that was given in the class. So let me go back to that. Yeah. So what you have is you can map this decimal and this binary value. So kind of this xi is nothing but xi min plus xi max minus xi min divided by 2 to the power l, say li minus 1 times this decimal or decoded value. So suppose I give you this x to be defined at intervals say 0 and 1, then you have to put 0 and 1s here. In place of x max, you have to put 1. In place of x min, you have to put 0. And then in place of L, you have to put 5 because you are using 5 bits here and you have the DVs already. And you can convert it into X. But suppose now I am not telling you to convert it because I'm not given you some ranges of this X's. So you can just directly take this as your X in this problem. So this will be your X values. And since fx equals to x, you will have the same thing here as well. And finally, you have to calculate the fitness. So that S of fx. So that you can calculate pretty easily. So these all add up to 20, 30, then and 30 and 40, 70, I guess. Yeah, this is 70. So this is nothing but 20. So that's fx divided by summation of fx. So this is 20 by 70, this is 10 by 70, this is 26 by 70, this is 14 by 70. And you can get the final values of this uh, strengths or the fitness factors. And they will add up to 1, of course. And using this, you can see this. This is the best solution that you have right now when you are trying to this maximize this function with this fitness function that you have. So I think this is not a difficult concept. I think so. These problems you are generally you have to generate a population pool at the beginning, or in this kind of problems that you'll be given, you'll be given a population pool, and based on that, you might be asked to have some sort of selection that you can do, or you can do then you can do take two solutions and do crossovers, and then you might take one solution and do mutation. So this crossover is always between two solutions, and mutation is just changing the bit around. So you can just have one solution and do that. And these are like, or you can like apply it to multiple solutions, those mutations and all, but you have to keep that percentages low and something. So typically, when you have, say, a 6-bit or 7-bit string, you might be like told to just flip one bit around. So the probability that you keep for those mutation may be 1 by 6 or 1 by 7, something like that. Okay, so let's see what else are there in the assignment. So this type of problem, I think you are familiar with. So as I have mentioned, the crossover, it's uh, generally convergent in nature because you are moving just two solutions around the parts of the solution and you are just doing some local search and your children is not far away from the parent, and if you already have got a good solution, then you are just checking if this is an improvement or not. But in case of this mutation, this where you are flipping this bit around, that plays a major role in your jumping of the solution, and that's why it's kind of divergent in nature. And yeah, so I think that. So the search techniques are like crossovers and mutations in this kind of setup. And selection, it's not a search technique. Selection is just selecting the best solution that you have. But again, there are certain limitations that you cannot create multiple copies of the best solution, because then if you do crossover, so suppose your selection gives you multiple copies of one solution, say 1010, then you suppose you have another solution in the set. But now suppose you do want to do crossover, but if you do this crossover between these two, if your crossover site is from this point onwards, so this goes here after this and this goes here. Sorry, this comes here actually. This comes here and this goes here. So then, even if you flip it around, you will get the same children in both the cases, and you don't do any improvement as such. So these type of situations are typically avoided, and that you can do, I think, is using just adjustments and those fitness factors and so on. And let's see what else I have left. So let next is, I think, the selection has a different thing, like selection, tournament selection I have already talked about. So the best solution will always win every round. So depending on how many rounds you play, you will finally get a like your best solution will have those many number of copies of it. But yeah, so your tournament size may be given as two, then you have to play only 2 rounds to generate those 6 solutions. But if you are increasing the size, then uh, suppose if you have a 6-bit string and you have, or maybe if you have 6 solutions in the solution space, if you are using 2 as your tournament size, then every round will generate 3 solutions because you will have 3 matches in every round. So you will need just 2 rounds to get to the initial number of solutions that you have. But suppose you're increasing, you have 6 solutions and your tournament size is 6, then it doesn't make much sense because in every round you are essentially playing the same match again and again. And then the best solution out of all will emerge as a winner, and you will create 6 copies of the best solution. So this is not a kind of a desirable result in that case. So next is the roulette wheel concept. So there, what you have, it's slightly different from what we had before in the tournament selection. So there you kind of go head to head, but now here you have some fitness factors associated with it. So suppose this is my solution, say 101, 100, 12, sorry, I think 2, okay. 1001. Suppose you have this 3 and you have the fitness of this, say 50. This is probably 60 and this is probably 90. So now your percentage of roulette will be calculated. So this is nothing but 200. And then if you divide it 50 by 200, that will be 0.25. Or since this is a percent, so I should write 25 here. So this is 25, this is 30, and this is 45. So these are the percentage of roulette wheel. So if you draw a circle, kind of, so the perimeter, so the 25% of the perimeter, so this 1/4 portion will be occupied by the first solution. Then the 30% of it, till this point, the second solution will occupy that, and the rest will be occupied by the third solution. So you're kind of assigning some probabilities to this. So the third solution has a probability of 0.45 to get picked, something like this. And you can convert this into expected count. So suppose you have 3 solutions here. So your expected count will be nothing but 3 times of this 25%. So that will be 3 times 0.25. So this will be 0.75. this will be zero point 0.9, and this will be, I think, 3 times of 45, so that will be 1.35. So now you have this expected count, but you need to get to the actual counts. So one way of doing it is just approximate to the nearest integer. In this case, it will give you same thing, 1, 1, and 1. But in actual cases, it might happen that it goes beyond this 1.35. It might be like, say, 1.6 or something. And the second one might be lesser than that as well. So you kind of decrease it and it becomes 0, and the other one becomes 2, something like that can also happen. So these are your actual counts, and they should add up to the number of solutions that you had. So now this is kind of telling you that this better solutions have a better chance of uh, preserving or like surviving in these cases. And what else do you have? So now you can have the rank selection technique as well, but that's one way of avoiding like creating a multiple copies of the same solution again and again. So suppose the fitness value of one of these was very high. Suppose this was say 90 or something, and the others had say 20 or maybe 5 and 5. So this had a probability of picked up by 0 0.9 with probability 0 0.9. But in reality, you don't want to create all these copies of the same thing. So the solution using this roulette wheel technique will have three of this as the best solution and zero of others. But if you use the ranking system, probably this might be ranked as one, this might be ranked as two, and three, and so on. So I think they provide this higher rank, this three rank, to the one which is having highest fitness value, and then you just put rank equals to 3 to 1, and then what you do, you add it up, that will be 6, and then you do this percentage. So this will be zero point 0.5, this will be 0.33, this will be 0.1617. So you kind of decrease the probability like this, and so that you have a good mix of the good solutions as well as a mix of the other solutions as well, so that you can use crossover techniques. So that's the main idea of using this rank-based method. So crossover I have already talked about. So when you have a binary string, it's simple. You just pick the site where you need to do crossover, and you can just perform the crossover and so on. Yeah. Do you have any? Uh, what is the binary crossover? Yeah, so when you have this binary string, suppose when I have say 37, so this is 16, okay, 8, yeah, this is 4. Yeah, so I think this has a decoded value of 37. Suppose I have another say 1 1 0 0 0 1. So this will have 1 2 4 8 16 17. Okay, so this will be some 49 or something. So this is your decoded value. This is your binary value. In case of binary crossover, suppose this is your selection site. You just bring this here, and probably this one comes here. So this is your binary crossover. The solution that you generate is this. But suppose I'm giving you this thing, this 37 and 49. Now, these are solutions, or maybe the solutions in the decimal values or the decoded values you have. One way of doing it is that you can convert it to binary and then do crossover. That's fine. But in the next class, you will probably learn that there are some real encoded crossover that might happen. So using this real value, how you can just generate a solution which is not far away from this two. So suppose this 37 and 49, some properties or some features you are taking from say 49 and including it to 37. Some features of 37 you are taking and then including it to 49. That way you generate some new solutions, maybe some average of this. Maybe it is in between these two, around 43 or something. That could be another solution that you create using this crossover technique. So that's the real encoded crossover. And the binary encoded one that I have already discussed, that's pretty simple. Just select the site and do the crossover. And this real encoded one have a lot of techniques. So there are many ways of doing it. You can introduce some probability distributions, and based on that, like drawing from that distribution, so you can do those kind of things. And I think it will be talked about more in the next week's lecture. And same with the another thing, which is the what is the last thing? Mutation. Yeah, the mutation one here, it is pretty simple. Suppose I'm given a string 10010, and I need to mutate this second bit. You just make it as 0. So it's as simple as that. But when I'm given, say, this is how much? 2, 4, 8, 16, some 18 or something. I think this one has a decoded value. And then suppose I'm given you this 18. Now I'm telling you how to do mutation on this. So that becomes a challenge, right? You don't want to get into the binary space and do this all these things. But if you're just working with real encoders, how you can generate a solution which probably flips one of these features around and you get to a new solution. So again, how you can generate a new solution from this existing one will be discussed in the next class as well. So yeah, those are the things that are more interesting and that's coming up in next week's sessions, and you'll probably get numericals related to that in the session. And I think since we have almost running out of time, so I think in the next week's sessions, I'll give an example of say maximizing a function which is sine uh, pi x. Yeah, correct. So this value is in radians, and I think your x is given a range of 0 to 1. So you know that sine function takes a maximum value of 1. So this is 1 when x is 0 0.5. So sine pi by 2 is the sine 90 degree, which is 1. So the optimal solution is say 0 0.5. But how you can get to that? So I think he solves one example problem related to that in the next week session, where he generates some solution pools. So first is just the solution pool. So he will generate, I think, some 6 of them using some random numbers or something. He'll probably select those with 6 bits. I think he will do that. And then with that, you can apply the fitness function. So since for a maximization problem, your fitness function is itself the function because you're maximizing it anyway. But in case of a minimization problem, your fitness function is something like 1 by 1 plus f. So there are many forms of this you can take. I don't know why sir has specifically chosen this. You could have chosen 1 by fx as well. But my case is when fx is strictly like non-negative or something, then this won't be infinity. You can evaluate the value. In case of here, if here fx becomes 0, this becomes infinity or something. So that's why probably that plus 1 comes in the denominator. So then I think he will apply this fitness values that I have already talked about. First, you have to decode it. Then you have to convert it. Since your 0 to 1, x is in that range, you have to take that equation, x min and x max. And using the decoded value, you can get the x values. And then you will put the fx, just plugging the sine function. Then you will get the fitness function, which is the same one. And using the fitness function, you might use some proportion technique or roulette wheel technique to generate a new set of solutions. So how many copies of which solution you build. And then you do crossover between, say, picking two solutions at a time, and you generate another solution pool. And then you do that mutation part, flipping the uh, bits around and get some new solution. And if you do all these things, you will be left with another set of six solution pool finally, and you can check whether you have improved your solution or not. If not, you can repeat the procedure again and again do some sort of decoded value, the selection technique, some crossover again, and do mutations till you reach the termination criteria. So I don't know. I think sir haven't hasn't talked about termination criteria yet, but it could be like some number of iterations or some like some good improvement in solutions or something like that. It fix. So this will be the main idea of all this, and with numerical example, with this one, I think it will be clear in the next class, and in the next session also, I'll probably take some similar examples and discuss the numerical part of this genetic algorithm more, because today's class was mostly, I think, concept based. So yeah, I hope you have understood this. So since it's already 4, and if you have any question, you may ask. Otherwise, you can join the other session that will be taken by the other team.